Alright, so in the last video lecture we started talking about characteristics of the periodic table, and we learned about one trend, which was atomic radius. This video lecture is going to go through a lot of the other different trends. And remember, it's not just memorizing what the trend is, it's understanding why it occurs. Okay, so the second trend of the chapter, and the first one I'm going to talk about today in this video lecture, is ionization energy. So what an ionization energy is it's the amount of energy required to pull an electron off of an atom. Remember, you have a positively charged nucleus, and so there is an attraction between that negative and positive charge. And so this is the energy required to make a positive ion. So when you make a positive ion, it's positive because it's short electrons. Remember, neutral atoms have equal number of electrons and protons, so when you pull an electron off, now you're short some negative charge, and the atom has an overall charge of 1 plus. That's if you're pulling off the first electron to make it short 1 electron. But remember, this requires energy, so it's considered a positive value for energy because you got to input some energy into it. Okay, so this is making what's called a cation. There's two types of ions. There's negative ions and there's positive ions. Right? Negative ions are called anions, and positive ions are called cations. You can think of cations because you like cats, and cats are positive. I'm not so much of a cat person, so I always think the word cation has a T in it, and a T is like a plus sign. Okay, so ionization energy is the energy required to completely remove an electron from a gaseous atom. I just realized I'm not even in slideshow mode, so I will do that. All right. So it's, remember that an ion is positive or negative charge. Removing one atom requires energy, and that's, if you're removing the first electron, that's the first ionization energy. So the second ionization energy, if you're already short electrons, if you've already removed one, and now the protons outnumber the electrons, you can bet that the second ionization energy is going to require even more energy. So if you remove the second electron, after it's already short electrons, you want to take one more, it's going to require even more energy. Think about it if I were the nucleus and I had cookies. Think of the cookies are like electrons. And I had one cookie for every kid in my class, okay? And then all of a sudden, someone took one of my cookies. They stole it. They removed it from my control. I'm going to be guarding the rest of my cookies, and it's going to be harder to take another. And if someone manages to take another, you can bet it's going to be even harder to steal a third one. All right, so the second ionization energy is the energy required to move a second electron. After one's already been pulled off, it's the energy required to remove a second one, and that's going to require even more energy. So it's always greater than the first ionization energy. The third is even harder, just like I explained with cookies. Stealing one cookie from someone when they don't necessarily suspect it requires some energy, but it's going to be a lot easier than if you want to do it again or even again. So the third ionization energy is even greater than the first or the second ionization energy. Now, there's a pattern here. If you look, these are first ionization energies. They are always lower than their second ionization energy, and the second is always lower than the third. But there are some interesting things that you see going on here. If you look right here, you see there's a cutoff. And what is significant is the first ionization energy for helium is very high. But for lithium, it's quite a bit lower. And you see the same jump here and the same jump here. What's happening at this line is, if you look, lithium right here, it's a noble gas. It is happy. It has a full valence shell. It doesn't. If you want to try and remove an electron off of that, good luck. Why is lithium so low? Well, lithium is in group 1. It only has one electron in its valence shell. And so if you remove that one electron, it achieves noble gas configuration. It would now, instead of being 1s2, 2s1, it will now just be 1s2, and it will have the configuration, the electron configuration of helium. It will have noble gas configuration. That means that it is a little bit easier to give it the configuration of helium because that's what it wants. Remember that electrons want to achieve an octet, so they want that. If you look at beryllium, Beryllium's in group 2, so it has an s2 configuration. If we remove those 2 electrons, it has a configuration of helium. So it's quite low. Now once it has a configuration of helium, then it's even, once it has a configuration of helium, so moving it from beryllium, the second ionization energy, is very, when you sorry, I'm going to start over. With beryllium, it has 2 valence electrons. Removing the first one, it's not that hard, but removing the second one is going to be much easier, because when you remove the second one, that gives you the configuration of helium, and that's why there's such a big jump. With lithium, it's such a high second ionization energy because after the first ionization energy for lithium, because remember it only had 1 valence electron, after the first ionization energy, it had the configuration of helium. If you want to remove an electron off of something that already has noble gas configuration, it's going to take a lot of energy, and that's why lithium's second ionization energy is so high compared to beryllium's. All right, so there are some trends here. I'm going to talk about those. So what determines the ionization energy? There are some factors. The greater the nuclear charge, meaning the more powerful the protons in the nucleus, the harder it's going to be to pull electrons off. Also, if you have more energy levels and you're trying to pull one off an outer energy level, that's going to be easier. So as you go down the periodic table, the ionization energy gets easier. It's easy to pick an electron off of like the 7th energy level way out in the distance than it is to pick one off the beginning. Think of my cookies. If I have a whole bunch of cookies, it's easier to take one off of an edge. I don't have as much control over the edge as I do the ones that are right in front of me. Okay? That whole idea is called shielding. What you have is, if you're talking about an electron that's in the 6th energy level, there are the electrons in the 1st energy level, 2nd, 3rd, and 4th, and 5th energy levels that all have a negative charge that sort of shield the effects of the positive nucleus. All right? So it's easier to pull electrons off when you've got electrons in between that kind of act as a buffer between the nucleus and the outer electrons. So here's the shielding, what I was talking about. Electron right out here has these layers of electrons that it has to see through to even experience any influence from the positive nucleus, right? So the more layers, the more shielding. So the second electron that's added here would have the same amount of shielding as this one right here. So group trends. As you go down a group, the ionization energy decreases. Memorizing just that alone is not enough. This happens because the electrons are further away and they experience more shielding. There's more energy levels in between those valence electrons in the outermost energy level and the nucleus. As you go across a period, all the atoms in the same period are in the same energy level, so they have the same amount of shielding. But something to keep in mind is, as you go across, even though there's the same amount of shielding, the atomic number increases, which means the number of protons increase, which means the nucleus becomes stronger. What that causes is, since the nucleus is stronger and has a stronger pull on electrons with the same amount of shielding, the ionization energy generally increases as you go from the left side of the periodic table, and as you go across, as the number of protons increases, the nuclear pull is stronger. So that means ionization energy is going to go up. It's going to take more energy to remove an electron. All right, so first ionization energies. Helium is much higher than hydrogen. Why? Because it has noble gas configuration. So has the same amount of shielding, stronger nuclear charge. Then lithium is quite a bit lower. Why? It has a lower ionization energy than hydrogen. It's in the same group as hydrogen. It's in group 1. But it has one layer of shielding. So it's the second energy level now. It's further away from the pull of the nucleus. And that outweighs the greater nuclear charge. So even though it now has 3 protons, because the atomic number of lithium is 3, it's now got some shielding, and that outweighs the increase in nuclear charge. But beryllium, same amount of shielding, has greater nuclear charge though, so you see an increase in the first ionization energy. Boron has a lower ionization energy than beryllium. It has same shielding, greater nuclear charge, but what happens is boron is S2P1. And by removing that electron from the P sublevel, it makes it so that it's just S2. Carbon increases, nitrogen increases for the same reason, but you break a pattern right here with oxygen because oxygen is P4, and if you remove an electron, it becomes P3, which according to Hund's rule, remember you have one electron in each orbital that way, so it's a half-filled P sublevel. Fluorine increases up to neon, and now neon has a really high ionization energy because it has an octet, and if you want to remove an electron from something that has an octet, and it's stable, and has a complete energy level, that's going to take a lot of energy. Okay? So it has more shielding, greater distance than helium, but sodium goes way down because now you've added an energy level. Way lower ionization energy than lithium. So what I would do is I would compare hydrogen to lithium to sodium. They're all in the same group. And you can see that the ionization energy goes down because there's more shielding. And then if you compare helium to neon, neon has more shielding than helium. But it does also have a lot greater nuclear charge, so you don't see a significant change. Those are the trends I would look at. Sodium and lithium, they're both S1, but sodium has more shielding, so ionization energy is different. Greater distance. All right, what you see here are periodic trends, and you can see up here they're really high because they have full valence shells, they have an octet. Down here, these are all the group 1 elements. This right here is the D block. So what you can see from this ionization energy, and this is a little above the scope of this class, but for those of you that are interested in this stuff, or you're taking AP or IB chemistry, this is evidence, these ionization energies are evidence of sublevels. This blip right here is evidence of the S orbitals, or the S sublevel right here and right here. This right here is evidence of the D sublevel. So there are patterns in the ionization energies that give evidence for why we know these sublevels occur. Okay, so driving force, full energy levels are very low energy. Noble gases have full energy levels, so they're very stable. Atoms behave in ways to achieve noble gas configuration. Second ionization energy, remember for elements that reach a filled or half-filled sublevel, removing a second electron or having a second, the energy for a second ionization is lower than expected. The reason for that, the reason why it's lower than expected is because it becomes more stable. So for S2, that's very true. What you have is, if you've already pulled one off, the second ionization energy is going to be lower than expected. It's still higher than the first ionization energy, but it's lower than you expect because what the second ionization energy accomplishes is noble gas configuration. It accomplishes that octet. So the alkali earth metals form 2+ ions. They are stable ions when you've removed 2 electrons from them. Why? Because it gives them noble gas configuration. It gives them that S2P6 stable electron configuration. Third ionization energies, same logic as for the second, except now you have S2P1 for valence. So if you remove 3 electrons off of an atom that's in that third group, that S2P1, it gives it noble gas configuration. You remove this 1 electron from the p orbital and these 2 from the s, and now you have a noble gas configuration, and that's very stable. So even though the third ionization energy is higher than the second ionization energy, it's still lower than you would expect it to be because it causes it to have a low energy to maintain like a stable configuration, low noble gas configuration. Okay, so atoms in the aluminum family form 3+ ions. The second and the third ionization energies, like I said, are always higher than the first, but sometimes the jump's just not that big between the first and the second ionization energy. And if you look at why, a lot of times that second ionization energy might cause an atom to achieve noble gas configuration, or something along those lines. Okay, so the next one is a trend. And I'm going to pause for a sec. So I'm going to stop right here, and then we'll continue on with other trends in the next video.